work. So, okay. So when I said I'd do it, we were waiting to hear a little bit about our climate resilience grand challenge. And we've heard, and they turned us down. We're going to resubmit, but we're hopeful for the future. But so I don't have a whole lot necessarily to say about resilience, but I will plug that in about at the end. Okay. So what I'm going to spend my time mostly talking about is essentially climate change. So I'm going to talk about topics here, science of climate change, what's the evidence for climate change, and then talk a little bit about projections and so forth down the road. Okay. So first of all, we always have to start off with the difference between weather and climate. The simple way to do this really is to say, well, weather is really an initial value problem and climate is a boundary value problem. So if you've ever thought about that, the mathematics of problems like that, weather is, okay, we better have really good understanding of what the weather is right now. And tomorrow's weather is probably not going to be that far off. The day after that, not far off. And so if you have the initial values and you can start to see how the physics and the dynamics of the atmosphere are going to interact to produce the future weather, you're in pretty good shape for a couple of weeks, maybe, it's outside 10 days. Okay. But weather's tough. Climate, on the other hand, is actually relatively, comparatively at least, relatively simple to figure out because it really depends on how much energy comes in, what happens to it as it bounces around, and how much energy goes back out, right? And ultimately, climate change is simply if there's more coming in than is going out, things are going to change, or vice versa. If there's less coming in than is going out, things are going to change in the opposite direction. So it's really a somewhat simpler problem. Now, the devil is in the details, right? The details of where things are going to change, how much, that makes studying climate change a tough problem. But really, you're looking at statistics over time, and it really is slower, changes much more slowly than weather. I mean, we've seen that quite, just in the past few weeks, right? It was freezing a few days ago, and now it's pushing 80. So, weather changes really rapidly, climate doesn't. Both of those things are actually within the climatological norms, so to speak. So, this is sometimes attributed to Mark Twain. There's no real evidence that he actually ever said it or wrote it. But climate is what you expect, weather is what you get, right? Or one of my colleagues over in the School of Natural Resources likes to say, well, climate is like the clothes in your closet. You have stuff for spring, you have stuff for fall, you have stuff for winter, you have stuff for summer, right? Weather is kind of what you decide to put on that day, right? You're going to dress for today. You're not going to dress for October, right? October, it could be cold. You have to, it could be warm. You have to know what's happening today, how you're going to, what kind of clothes you're in. Okay, so what about climate variability? There's a lot of variability within the climate system and climate change. There's a couple of terms that we banter around a lot. And climate, we usually define in terms of these 30-year means and some higher order statistics like variability and so forth. But really what that assumes is that the climate, at least statistically, is stationary. It's not changing, right? The statistics aren't changing over time. And that's what we found recently is not the case. I mean, a longer period of time, things do change. I'll trip over this chair. So variability, we have to think about in terms of shorter time periods. Climate varies there's different patterns like El Nino that happen on certain, on kind of shorter time scales that affect the climate system quite a bit. And then climate change, we like to think of as variability that happens on the longer time scales, okay? The distinction comes somewhat arbitrary. So usually when you talk to somebody who's studying climate change, which is where most of my research is these days, the distinction is arbitrary, and we usually lump the two together. We talk about climate change and variability, climate variability and change lumped all together. Okay, so the climate system is more than just the atmosphere. It's more than just the statistics about weather. There's many components: the cryosphere, ice, either on land or in the ocean, floating in the oceans. The land itself. If you really want to study climate change, and Kevin alluded to work I did back looking at modeling the climate of the Jurassic, well, the continents weren't even where they are now back then, right? They were all lumped together into Pangea, and that changes the circulation systems that you see. It changes the heating and cooling in different parts of the world. And so you have to take that into consideration if you're dealing with either distant past climates, or in some ways, even now, in terms of sea level rise, sea level recession, and so forth, that can change where the coastlines are, right? The hydrosphere, what's water, what's land, how much water is in the land, right? Soil moisture stuff. Those things are all part of the climate system. The biosphere is as well. We can see cycles that are based on growth of plants and dying off in the following year. You see those kinds of things linked to the seasonal cycle, and also have a role in feeding back into the seasonal cycle of weather and climate. And then finally, of course, the part I study most is the atmosphere, the thin shell of gases around the planet. Okay? And so I always like to get this up. This is the simplified conceptual framework, right? And actually, I had another one that was somebody had put together decades ago that was supposedly simplified it as well, and it was even more complicated. But you can get, again, all these things go into leading to what is the climate of the Earth, or the climate of different places on Earth. And so we have these forcing agents. I'll talk more about them in a little bit. And we also have feedback processes, and that leads to a lot of complexities once you start looking at feedbacks, right? So all sorts of things, indications of climate change is taking place. You know, are there changes in the amount of radiation coming from the sun? Yes. Are they important in what we're seeing in climate change today? Probably not. Okay. Partly because it's somewhat cyclic, and we haven't seen any great trends, and the forcing itself is rather small. We'll see. Changes in the surface properties, changes in heat uptake by the ocean, and so forth. All these things are part of the climate system that we have to study when we're thinking about climate change. It really comes down to this. Okay, this is the Earth energy balance. Okay, like your checking account, right? You got money coming in, you got money going out, right? Well, the Earth has energy coming in from the sun, and we emit energy back out to space. Okay, if that's in balance, then we would expect the global temperature, the temperature of the Earth, if we could kind of decide what one temperature represents that, the temperature of the Earth shouldn't be changing, right? And so this is the very fundamental part of our system and our study of climate change, right? So we can see 340. This happens to be in watts per meter squared. So this is 1 watt per meter squared is about, I think, two of the little holiday lights that you might have on your tree. A couple of those per square meter, right? That's 1 watt per meter squared. Each of those is about half a watt. So, 340 coming in. That's averaged over the entire surface of the Earth, over the entire day, over the entire year. This is what's happening. 1 joule per second per meter squared, or 340 of those. About 100 is reflected out by the surface and clouds around Earth. So we have about 240 to work with. Some of it gets absorbed. Actually, only about a third of it gets absorbed in the atmosphere. Most of what gets absorbed actually gets absorbed at the surface, which heats up the surface. Okay. Now things get interesting, right? Because now the surface is going to warm up, and you've got this atmosphere that has gases in it that we call greenhouse gases, because, not a good analogy, but because they absorb energy given off at long wave, okay, not visible wavelengths, that then are absorbed by the clouds, by the gases in the atmosphere, and then that heats up those, and then they give off energy back out to space. Okay, and you can see that. Great. Okay, we've got 340 coming in, 100 reflected out, 239. We're pretty much in balance. Okay, I'll talk about the imbalance in a second. Pretty much in balance if we just look at that. But those clouds and gases in the atmosphere, of course, are not they're not emitting energy just out to space. They're emitting energy back down to the surface, which adds to the heat budget of the surface, which now has to figure out a way to get rid of more energy, right? Because it only had 160, but somehow it's able to give off almost 400 watts per meter squared of energy. Well, that's the extra 342 over there that's coming down. And if you start talking about just the radiative exchanges between the Earth's surface and the atmosphere, we're still not in balance. And so we have the things that make me happy, right? Evaporation and sensible heat. Why is sensible heat thing a little spirally line? It's convection, like thermals, right? You know, that's what makes people in my business, weather and climate, exciting. You know, this is a terrible weather day today. Nothing's going on around here. We hate it, you know? What we want is an exciting weather day, like either there's severe storms, there's a blizzard coming, or something like that. That's interesting, right? So, you know, we got caught one time by a former D on the roof of our building. He wasn't on the roof, but we were on the roof of the building during a tornado warning, and we were told we weren't allowed to do that. But it's like, that's what we do. We run out to see those things. All right, so in general, we do have this balance, and it's pretty close. But there's that 0.7 watts per meter squared imbalance currently. Okay? About 1.5 of those light bulbs per square meter, right? Not much, but it's on day and night. It's on 365 days a year, and it is an imbalance. And that's causing the Earth to retain more energy than it's emitting back out to space, which it'll do. It's going to heat up the system. All right, so what's really important, what it comes down to, are these forcings. And so far, I haven't really talked about any kind of forcings except for that solar forcing that's really not very big. But that's an external factor, something outside the system, the climate system, that is either natural or anthropogenic. So it might be solar variability, it might be volcanic eruptions. We have more energy coming from the sun, we would expect things to heat up. If there's less energy coming in from the sun, we would expect things to cool down. If we have volcanic eruptions that reflect more radiation back out to space, that should be a cooling. That's what we've seen in many past large volcanic eruptions. Or the anthropogenic ones are largely things like greenhouse gas emissions. Okay, the greenhouse gases, carbon dioxide, methane, nitrous oxide, lots of other things. And then land use changes. If we change from a forest, which doesn't reflect very much radiation, to a grassland, which might reflect more radiation, we would expect local cooling. Okay, so those kind of things. If we do something that causes the land to dry out more, okay, that might change the heat balance that we expect to see, at least locally, if not globally. And then, of course, feedbacks, which I'm sure you're all familiar with, are something that's internal to the system that modifies a forcing. So if a forcing pushes the climate in one direction and there's a negative feedback, the system would try to restore itself. If there's a positive feedback, it'll keep going in the same direction. Of course, the typical thing I always tell non-scientists when I'm talking about this is that that we are all familiar with feedback in terms of microphones and speakers, right? You get the microphone too close to the speaker, anything you say gets amplified, goes back in the mic, comes out even louder, and you get that big whining noise that we all hate, right? That kind of positive feedback is something you have to come up with another way to address. In some cases in the climate system, some things could be a forcing and a feedback at the same time. So I said there's anthropogenic forcings, right? Things like if we add CO2 to the atmosphere, that's a forcing. It's going to cause changes to the system. Okay. But as you increase the Earth's temperature, because you added greenhouse gases like CO2, and the oceans warm up, the oceans then can release carbon dioxide because of the warmer temperature, they can't hold as much in saturation, right? So then that becomes a feedback, in this case, a positive feedback. And this has happened in past climate change, natural climate change, where we see temperature warming for some reason in the system. Usually it's because of orbital changes or something like that, changes in the ocean circulation. And then shortly after the Earth starts to warm up, you see the level of carbon dioxide in the atmosphere start to go up. And then you've got now a feedback because you then store more energy in the system because of that enhanced greenhouse. Okay. We see the global temperature rising. It's been rising over the entire instrumental record. So the last part there, the blue part of the curve here, since about the late 1800, mid to late 1800s, we've seen temperatures going up and up and up. Thermometers out there around the world, temperatures have been going up, and lately it's been going up dramatically. And if you look at the changes that we have from proxy records, these are largely tree rings and isotopes from ice cores and things like that. We can go and estimate the global temperature back in the past, and we can see that temperatures have not been, over the last 1,500 years or so, been higher than they are now. But I think what's more important on this is that the rate of increase that's been happening in the last 50 to 60 years is much higher than the rates of increase that we've seen in most of the proxy records. We can look at, again, this is now just focusing on the instrumental record that we have over the last 140, 150 years here. And we can see that this is now, these are departures, anomalies, we call them, from the average over the entire 20th century. Okay, so we can take these and plot them out, and we can see that the early part of this record, starting in the late 1800s, was consistently cooler than today. Temperatures were, global temperatures were 1/4 to 1/2 degree cooler than they were over the 20th century as an average. And over the last 50, 60 years, the temperatures have been consistently higher than that average. Okay, and there were some periods in between the big blue and the big red out there where it kind of goes back and forth, but it's close to the average. And what's important for us, one thing I always like to point out here is, you know, when I talk to most lay people about climate change, they think about what their parents might have experienced or their grandparents might have experienced. They say, oh, what about the Dust Bowl in the 30s, right? It was really warm during that period, wasn't it? Well, it wasn't in the US, but there's the 30s globally, right? And we have to remember that you have to look at the entire world. If you're going to do these kind of energy budgets and look at climate change, you have to start out by looking at the entire world. And the whole world was not hot and dry in the 30s. The central US was, sure, but that was the case. The other big period, another big period that people always bring up is the 50s, right? And so there's the 50s again. 50s were quite warm and dry in the United States. In fact, actually, by a lot of measures, it was worse than the Dust Bowl, but we had figured out some ways to handle the conditions that we experienced during the 30s. And so it doesn't come up in the popular imagination, perhaps, as much. But it was, for the globe, the 50s were actually a relatively cool period. Okay. So let's see if I can get this to work. This is just now a reconstruction from NASA of temperatures over the last 140 years. Okay, and so what we're going to look at is these are 5-year moving averages. So this is the global temperatures 1880 to 1884, and we'll go up through the end, I guess, of last 2020 to 2020. And these are now temperature departures from a baseline from the 50s to the 80s. Okay? And so you can see most of the globe back in the early part of this movie we're in the blues, right? Quite cooler than what we see in the 1950 and 1980. Some areas you see some now we're getting up into the 80s. Things are starting to get warmer and warmer and warmer and warmer. And then all of a sudden in the last few decades, right, you see that pronounced warming. And you see that it's not uniform around the globe, right? But it is, most of the globe is quite a bit warmer than it was between 1951 and 1980. It's a 30-year period that we always define as climatologists as a normal, right? But you can see that the Arctic has been an area that's warmed up considerably more than most other areas. There's a couple patches here and there of cooling, right? There's a cooling area in the North Atlantic, south of Greenland, that's related to the ocean circulation. Okay, and that tends to stay has been cooling because of the atmospheric circulation changes that have taken place and the melting of ice off of the Greenland ice sheet. And but in the Arctic area where we see the bright reds, this is an area where we have extreme feedbacks, right? This feedback is what we call the ice albedo feedback. You start melting ice, sea ice primarily over the Arctic Ocean, but also some land ice. You start melting ice and snow, where the seasonal snow, if it melts earlier, then it exposes darker surfaces under it, right? Ice and snow are pretty white, highly reflective. You start melting that off, the oceans themselves absorb a lot of radiation, and so do dark land surfaces. And that's a positive feedback effect that drives this extreme temperature change. So there's lots of things. This is from NOAA primarily, the National Oceanographic and Atmospheric Administration. Every 5 years or so, we do a national climate assessment, and we've been seeing that all the indicators that they follow, the temperatures over land, the temperatures in the atmosphere, the amount of water vapor in the atmosphere, sea surface temperatures, sea ice, sea level, all these 10 indicators here are all, they're not all going up, right? Because some of them are going down, but they're all going the direction you would expect if the climate was warmer. Okay, so we see it in the temperature record. We see it in these other records: glaciers and ice sheets, snow cover decreasing, sea ice decreasing. One of the things that I always like to point out, I don't have it in my slides, but how many people are gardeners? Any gardeners here, right? And you buy those seeds from Burpee, and then you look at the back, and there's always a picture of what zone you're in, right? Those are changing. They've changed over Nebraska. We've, over the last 30-ish years or so, we've shifted by a half to a full zone across Nebraska. It changes what we can plant, what we can grow, all those kind of things. And people, sometimes people who are skeptical of climate change will say, well, the cities are getting bigger, and the temperature instruments that you have are all in the areas that are getting concreted over, and that's why it's getting hotter. Well, seed packets aren't showing the same thing. They're showing what you can grow, and the plants are out there away from those areas, and we're having to change what we can grow in parts of the world. So how do we know it's caused by humans? I think, that's the next big question, right? Most of the lines of evidence we have really point this way, right? The Earth's surface temperature has clearly risen over the past 100 years, especially in the last 50 years or so. And that's the time period where humans had really driven up the carbon dioxide levels in the atmosphere, the carbon dioxide being the prime greenhouse gas. Okay, so here's the carbon dioxide concentration and global temperatures. I don't generally like these because all you're doing is overlaying, shift them around, you want, right? And it's going to look pretty dramatic. But nonetheless, CO2 levels are much higher than they were pre-industrial revolution, and now we've got to deal with that. Plus, the temperatures that are going up are doing things like, in that earlier slide, increasing the water vapor in the atmosphere. Water vapor is even a more potent greenhouse gas than is carbon dioxide. And that's a natural feedback. You increase the temperature, you evaporate more water, the atmosphere is warmer, the saturation or the equilibrium level of water vapor in the air is higher. And so you have more water vapor in the air, it's a greenhouse gas, it absorbs more of that long wave radiation coming off from the surface, and you get more heating down at the surface. So there's a really big feedback process. And it's one of those things where another criticism you'll hear from skeptics is that, oh, and we'll talk about climate in a minute or two, but they'll say, oh, those climate models, you don't adjust the amount of water vapor in them. Well, we don't have to. All we have to do is let it heat up, and we get evaporation from the surface, and it'll increase the amount of water vapor in the air. So we don't play with it. We don't have to. There's no water vapor knob we can turn on the models. It happens automatically. The basic physics of the greenhouse effect. This is nothing new. I mean, physicists started talking about, they didn't call it a greenhouse effect back then, but they talked about how increasing carbon dioxide in the atmosphere would change that radiation balance. When did they start talking about this? Anybody know? Back in the 1820s, right? This has been around for a long time. People started doing calculations of the amount in the late part of the 19th century and early part of the 20th century. I think one of the key things to me is that really nailing down that it's humans and human emissions of greenhouse gases is the fact that physically we should expect that the lower atmosphere, or what we call the troposphere, the lowest, say, 12, 15 kilometers of the atmosphere, where we happen to live, right, should be warming because it's closest to the surface that's heating up, right? It's closest to the campfire, warm up more, right? But also, if we're capturing more of that emission from the surface in the lower part of the atmosphere, it's heating up. There's less radiation getting into the next level of the atmosphere, the stratosphere, and it's actually should be cooling off, and it is. Okay. Now, why do I say that's important to know about whether humans cause it or not? Because if the sun were the primary driver, the whole atmosphere would just be heating up. Okay, it wouldn't matter. You'd be heating up the ozone layer, you'd be heating up the surface, the whole thing would heat up. Okay, evidence shows that in fact that's what we see. The lower stratosphere has been cooling. These are satellite observations up to about 2012 time period, and then excuse me, those are satellite and radiosondes, balloons that we send up for both of these. And we see cooling in the stratosphere, warming in the lower atmosphere, the troposphere. Okay, so it matches. So it's kind of a fingerprint for me. And then when we start using computer models, we see that we really can't reproduce the warming that we've seen unless we incorporate the greenhouse gases that we've been emitting and increasing the concentration of in the atmosphere. So this is another one. This is one that I think convinced a few of my friends over the years that if you do computer modeling, nice thing is you can turn things on, turn things off in the model, right? So you can say, okay, let's not worry about humans. Let's assume that the CO2 level is the same as it was pre-industrial revolution, and we'll run our models. And that's the top figure here, where you can have some of the variation that's caused by volcanic processing, solar variation, and so forth. And they kind of just bounce around that zero change line, and they don't match the observed temperature trend that we see, right? That's the black one, okay? If we look at, then down at the bottom, we look at, excuse me, in the middle, if you look at the human influences, we come closer in the middle, right? So all human drivers, the red line there, it's pretty close to the black line. It doesn't vary as much though. It's a trend, not climate variability. You put them both together and we're pretty much spot on in the bottom. We have the brownish gold line there is both natural and human influences and the observations. And we can match them in our models if we include all those forcing. If we include just one or the other, we're not going to be as accurate. Okay. Again, looking a little bit more clearly, these are measurements. Here's the temperature at the top, the solar component. You can see there's a slight trend in solar input over the last 100 years or so, 150 years. But more importantly is the 22-year cycle that we see there. But even over this period of the last 50 or 60 years, at the end there's not much of a trend. There's a huge trend in the temperature, right? A volcanic component, well, what the heck's that? It's going the wrong way, right? Every time we have a volcano, it tends to cool off the climate system. So that really is not going to be a cause of warming. Natural variability, and that lumps in things like El Niños and other big circulation events around the world. What's called the Atlantic multi-decadal oscillation, those kind of things, these big trends, these big variability variations in the atmosphere over time. The only thing that we can really say that's had a trend over the time period where the temperatures have been going up has been this anthropogenic. Okay, so we like to do experiments, right? How do you do experiments when you only have one Earth, right? We're doing an experiment. Unfortunately, we don't have a control, right? That's the big thing. So we have to use numerical models. It's really our only opportunity to try to investigate what might happen in the future. Okay, so we don't have the ability to do anything by putting the Earth in a beaker or something, right? So I brought a model. Okay, this is it. Okay, this model is really simple. We're going to have a ball. We'll call it Earth. Okay, it's 150 million miles from the sun. 150 million miles. 93 million. The sun gives off a certain amount of energy. It strikes the Earth. Okay. Well, This is where I freak out my students, right? Because they say, well, we have to integrate this over the surface of the earth and stuff like that. And they're like, oh, and I say, no. What we do is we make a simplifying assumption, right? Think about if you hold a ball, Earth, in front of a projector, right? What do you see behind it? You see a shadow, right? What's the shadow look like? A circle. What if I hold a disc the same size? What are you going to see? A circle. Okay, now I can hold that disc so it's at right angles to the projector, right angles to the sun. I don't have to do any real work. I don't have to do any real math. All I have to know is how much of the stuff coming from the sun, the radiation coming from the sun, hits that circle. Boom, I got it. That's easy. Okay, so I actually can figure out that what's coming from the sun is 1,368 watts per meter squared. The Earth has an albedo of about 30%, 0.3. So we reflect we reflect 30% of the radiation that strikes us away. We absorb 70%. Okay. So if we take the rate, multiply it by the area of that disk, okay, we know how much energy we're absorbing. The other side of the equation is how much we give off, but now we're giving it off. We had to go back to the ball. We're giving it off evenly from the entire ball. If the Earth has one temperature, it's going to emit radiation equally in all directions. Fine. So we need the surface area of the sphere, put those things together and solve for this F sub E. Turns out that we need to get rid of 239.4 watts per meter squared from the Earth to stay on radiation balance. Okay. Well, now we can use something that was discovered again back in the latter part of the 19th century, the Stefan-Boltzmann law, which says that the amount of radiation that an object gives off, if it's a black body, is a constant times the temperature to the fourth power. We can invert that around and we can figure out what the temperature has to be to emit that amount of radiation. And it turns out the temperature is 255 Kelvin, minus 18 degrees C, roughly around 0 degrees Fahrenheit. The Earth is not frozen. Okay, right? We know that. Okay, so this is too low, but this is what it should be if we don't have an atmosphere. That's what we call the equivalent black body temperature of the Earth. Now, what do we always hear about greenhouse gases? Well, the atmosphere is transparent to shortwave radiation, solar radiation, and it's opaque to longwave radiation. Well, neither of those things is totally true, but let's use that, okay? Let's put in a very simple atmosphere. So here I've drawn a little picture. I've got the sun coming in, it's sending in a certain amount of radiation, F, and that means if the atmosphere, the blue thing there, is completely transparent, F is going to come out the bottom of the atmosphere and hit the surface, okay? We assume that all that energy gets absorbed at the surface, okay? In other words, the surface is a black body, okay? Then it has to emit, it's going to warm up and it's going to emit radiation. Well, to have a balance, okay, I'm shortly sure. To have a balance, we have to be emitting F amount of radiation, long wave radiation, back out to space. As I said earlier, if the atmosphere is emitting radiation up, it's also going to emit radiation down. Well, if the atmosphere has a certain temperature that allows it to emit F units back out to space, it means it's going to emit F units down to the surface. And now the surface has to get rid of 2F, okay? One from the sun, 1F from the sun, 1F from the atmosphere. That means the surface has to be hot enough to emit 2F. And if you work out the math from that, it turns out that the surface temperature of the Earth should be about 303 kelvins, okay? About 85 degrees Fahrenheit, higher than what we just showed a minute ago. Okay, 30 degrees Celsius higher than what we said a minute ago. Well, or excuse me, about 30 degrees Celsius. That's too warm. Okay, now we got this Goldilocks issue, right? One model's too cold, one model's too hot. Well, it turns out you can make more realistic assumptions, okay, about the atmosphere. It's not totally transparent to shortwave radiation. It's not totally opaque to longwave radiation. It's a big chunk of the atmosphere that lets most of the radiation go right out to space at certain wavelengths. And so if you start making those more realistic assumptions in your model, you're going to get closer and closer to the true atmospheric temperature, the surface temperature of the Earth. Now, it also means the other thing you really need to do is add more layers to the atmosphere. It turns out that you can come pretty close to the actual temperature we would expect to see, as long as you do one more thing. Okay, just to get the surface temperature right, you have to remember that little red spiral ahead and the evaporation part, right? You have to have other mechanisms to transport energy from the surface to the atmosphere. And both of those things, evaporation and convection of sensible heat, both of those are cooling processes at the surface, and it allows you to really hone in onto the actual temperature, something close to the actual temperature. Of course, what is the actual temperature there? Well, we don't know, because we've seen a couple things there where multiple data sets would disagree. We don't have perfect measurements of the temperature of the Earth. It varies over space, it varies over time, but we have a pretty good handle on what the average temperature is. So back to those components of the Earth system, how do we make the model better and better? We add these components to the model. No longer just a simple atmosphere, we start adding things like the land surface, how it interacts with the climate system, sea ice, land ice, the oceans, okay? All those things then now go into a much more complete, much more complex model of the atmosphere that also allows transport of energy from areas where there's an excess of energy horizontally to areas where there's a deficit. So we transport energy from the tropics to the polar region. So we need to have these kind of high level dynamic models. And so what we do, we divide the whole Earth and atmosphere up into little boxes, and we figure out what's going on in all the boxes and how they exchange energy and mass between them. And we have a global climate model. Okay, it's also a weather model too, depending on what kind of time scales you're on. Same, they're very, very similar. Okay, we started out when I was in grad school back many decades ago. We did have rain. We did have carbon dioxide. The rain came out of the air. We didn't have clouds. We had rain. Okay. We had to get the rain. We had to evaporate to cool the surface, and we had to have the rain to bring the water back down to the surface. So we did that. It wasn't until the mid '80s when I was actually a young faculty member here that we started putting clouds into these models. Okay. And then by the early '90s, we actually said, oh, we should have an ocean too. That's a good idea. We used to just kind of have wet surfaces. They were, what they were. So then we added an ocean. It was basically a swamp. It was basically a sponge. It was a wet sponge, right? You couldn't move stuff around in it or anything like that. So it wasn't until the mid '90s that we started to get ocean circulation. It wasn't until the early 2000s that we actually started to do other things like incorporate a carbon cycle, because we know that carbon dioxide goes up and down every year as vegetation grows and goes into senescence and decay. And then by the late 2000s, we started thinking about, oh, what about atmospheric chemistry? What about these things these molecules that are floating around? What happens when they change? They join together, they make aerosols, they do all sorts of things. That's important too. And so we made much more complex models, and I don't even have an update here. We're now looking at these various acronyms. FAR is the first assessment report from the IPCC. SAR is the second assessment report. TAR is the third assessment report. We probably would have gone back to FAR again, but they realized that would be confusing, so they said we should use numbers. We don't run out of it. We only have a certain number of letters. So they went to AR4, the assessment report 4. Assessment report 5 came out in 2013-ish. And now we're working on assessment report 6, which has the early drafts are out. They're still working on the final wording, but they're not going to change. And we have these much more complex models now that take into consideration many of those aspects, the components, the vegetation, the ice, the atmosphere, the oceans, coupled together. We've also included we made the boxes smaller. Okay, so this is the first assessment report back in the mid '90s. We're looking at this. You can't tell where this is, right? You can't tell what the heck is it. Where is that? Well, if you start looking into the future here, you might start to see, oh yeah, this is Europe, right? This is Greenland here. Where's Iceland? I don't know. this here, the boxes were the size of Nebraska. You want to get a good handle, okay, essentially. Well, actually, two Nebraska stacked north and south. That's approximately the size of these boxes. And we know that there's a lot of difference between what's going on in eastern Nebraska and what's going on in western Nebraska, what's going on in South Dakota, whatever. The boxes were way too big, but they still told largely the same story. So over the years, we've gone to finer and finer boxes, and we're seeing better representations of the climate system. By the last assessment report, we were down to less than 100 kilometers on the side for the boxes, but that's still really not a lot. That's eastern Nebraska. Okay. And so a lot of people, including myself, have been trying to use what we call regional climate models, or RCM, to downscale the large global system because it's linked to the boundary problem that we talked about earlier. That's what's driving the big model, climate. And now we can take a regional model, basically tuck it inside a global model, have the energy fluxes across the borders now, and top and bottom, all four sides, energy and mass coming into there, and we can figure out, we can really treat the dynamics of the system at a much higher level and get better, hopefully, predictions of what's going on. Because if you're somebody who's interested in climate impacts and trying to build a resilient, I'm going to get this in here, build a resilient system, right? You need to know what's happening at a much finer resolution than global models can ever give you. I've worked for a long time with a colleague in Latin America and the Caribbean with policymakers and people on the ground who are trying to figure out how to create a resilient system. And they always want to know, well, what's going to happen 30 years from now, in terms of something that's going to affect my city's storm sewer, right? How do I build a storm sewer system? I have to know whether we're going to get more precipitation or less precipitation. Well, you're not going to get that from the global climate. It doesn't tell you the 8 to 7 kilometers. It doesn't tell you what's going to go down your drain. So we use these regional climate models, like I said, that are basically driven by the conditions bound by the global. And they take all the energy fluxes. So this is kind of, a box made up of little boxes inside, but we have the energy fluxes, the mass fluxes coming in from all four sides of the model. And we can drive using the physics that we understand in the atmosphere, physics of thermodynamics and dynamics, and try to figure out what's happening regionally. Okay? And so this is the kind of stuff we get. If you look at this is a relative 300 kilometer resolution global climate model, that's what we would say would be happening in terms of precipitation over this region. You get down to 75 kilometer resolution, you're actually starting to see things like, oh yeah, there's mountains there. That makes a difference, right? When it's raining, when wind goes up the mountain, it cools, it rains. You start to see that better when you get down to 50 kilometer resolution, and you're getting somewhat closer to what you expect in terms of the actual precipitation over California with the mountains and desert. Again, going back to these projections of future climates, climate models have been shown to reasonably reproduce present day climates if we include all the known forces, natural, human, okay, and all the processes that go on in the atmosphere, as many as we can. They're based on our best understanding of the interactions within the climate system, the dynamics, the thermodynamics, and the physics of these systems. All right? They work for the past. So what can they tell us about the future? Well, my argument always is that, well, I don't think the physics is going to change. Our understanding may change a little bit, but I don't think the underlying physics of thermodynamics is going to be different in the future. At least not, not unless something really. So I think the models can be used to make projections about it. The trouble we have is that it's making projections about the future is not completely based on physics alone. It's based on humans. Okay? And I have a lot more uncertainty in what humans may do over the next 70 or 80 years than I do what's going to happen to the physics. We just don't know. Are we going to get our act together? Are we going to decrease the emissions of greenhouse gases? Or are we just going to keep on happily burning as much fossil fuels as we can? So what we do is try to come up with what we call scenarios. What are possibilities that might happen? And so this underlies the Intergovernmental Panel on Climate Change, the IPCC. It underlies their projections of what's going to happen. Are we going to come to some agreement that we should at least not add any more CO2 into the atmosphere over the next for the rest of the century? Or are we going to try to cut it down a little bit? Maybe we're going to go up for a little while, then start coming back down, or are we just going to go merrily along in our way? Right now, we're going merrily, pretty much, but we'll see what happens over the next few decades. Right? If this is the case, then let's start looking at what might happen. This is now temperature differences, end of the century versus the end of the 20th century. Okay, and you can see that if we do this rapid emissions reduction, what's called this representative concentration factor 2.6, it means that we limit the radius of forcing to 2.6 watts per meter squared at the end of the century. We can see that things don't look so bad. We're able maybe to keep things down to, except for maybe in the Arctic, down to just a few degrees Fahrenheit. You have to bear with me because when I use international box and stuff like that, they always assessment. The National Climate Assessment. So you have to bear with me. Precipitate, but if we don't, and we follow the path that we're on now, we're going to see very large 9, 10, maybe even higher temperature changes across large parts of the grid. Precipitation, I will freely admit that we do a lousy job at modeling precipitation. It's tough. Okay, it's a tough nut to crack for weather, let alone for climate. Okay, there's a few things that we do pretty well. One thing we can say is that we think areas that are going to get wetter are likely to get wetter because it's going to rain harder when it does. Okay, and that follows the physics that if there's more water vapor in the atmosphere and it rains, you're going to make more rain. So yeah, if the conditions are right to get rain, you have the available water vapor in the atmosphere to make more rain. So we expect to get more intense storms. Okay, that's actually showing up already in some of the data in certain regions. But it's really hard to say what's going to happen. And of course, if you look at some places in the mid latitudes like us, right? We're somewhere in the maybe, who knows? You know, that's a lot of it. In fact, if we focus in, which we'll do on North America and the U.S., you'll see that as exactly. So Nebraska, somewhere on the low end, 4 to 5 degrees warmer at the end of the century, 8 or 9 or more by the end of the century. At the higher emissions, again, that's what a human's going to do. A lot more high temperature days, over 100 degrees, than we have recently. What's really disturbing to a lot of agricultural people, especially people who raise livestock, is that the expectation is that we'll have many warmer nights. We're not going to cool off at night as much as we want to, and cattle and other livestock do not respond to not. They can handle a hot day if it cools off. Okay? But if it doesn't cool off at night, it makes it harder for them to handle multiple days in a row. Frost-free season looks like it's going to get longer. Great if you're a gardener, you can start earlier and harvest later, right? As long as you have a lawn. So again, looking at just North America, we can see these kinds of things. I think we're right now on track. We're on track for the higher scenario, and by the end of the century, we're looking at 7, 8, 9, 10 degrees warmer in our area than we have today. Precipitation, like I said, it's pretty uncertain, but the changes tend to be larger in winter and spring compared for our region. Well, in the winter, we don't get a lot, so doubling the amount we get is still not a lot. So it doesn't really help very much. In spring, sometimes we get too much in certain areas, and so that's a problem. Probably smaller changes in the growing season, that's not good either. More periods of heavy precipitation, okay? Those are all potential problems for us. I did a study with a colleague of mine a few years back, a groundwater geologist. And we looked at what might happen in, for example, the Sandhills, a very unique area for our state, right? And the interesting thing was, and I'm not quite yet ready to bank on this, but looking at some of the scenarios projected for precipitation in the future, again, these larger, maybe less frequent but heavier rains in the Sandhills, that's great, right? Because it's sand. What happens to the water on the land? It just goes right through the upper layers where it can evaporate, and it becomes distant from the atmosphere. And it soaks in and adds to the groundwater. So perhaps we can come out in that respect a little bit ahead. We're going to have greater groundwater recharge. If you look at the Ogallala Aquifer, the High Plains Aquifer, which stretches from Nebraska down into Texas, Nebraska is the part that hasn't really suffered from over pumping and losses, like everywhere from Kansas south are really depleting the aquifer. Our aquifer just keeps recharging largely because of the sand and other sources. So outside of the sandhills, though, we do expect that soil moisture will probably decrease. Right? So, seasonal precipitation, like I said, probably higher in the winter and the spring, lower in the summer and the fall. Lower in the summer is problematic because of the growing season. In the fall, probably good not to have too many huge changes, but this is still a long way out. And like I said, we don't do precipitation all that way. Okay, soil moisture probably decreasing over most of our area. Some of these models that they use for this do not recognize the sandhills as a kind of a unique area. So we kind of put that in. Okay, so I started off, we brought this up. This is my opening slide, right? And I mentioned that I didn't have a lot to say about resilience, but I do have a few. Okay? I think there's a gap, right? There's a gap between the size of the climate problem and our efforts right now, at least to address it. So what we need to do is close the gap. And this image is from the Union of Concerned Scientists that have put a lot of thought into climate and climate change. And it's trying to reduce this gap, okay, to create more resilience is going to require multiple things. We're going to need to reduce the causes of climate change that are caused by humans, and then to mitigate the causes. But we also have to figure out ways to adapt to what inevitably is going to happen, at least over the short the next 30 years or more. Okay. But I think one of the interesting things is that we need to figure out ways to do this, thinking about equitable solutions, right? Not because a lot of the harm from climate change gets pushed onto disadvantaged communities, right? I'm not too worried about the U.S. as an economy, for example. We'll figure out ways. I'm worried about places like Bangladesh, right? Pakistan, India, all these places. There's a lot of people there, and they're getting hit hard by climate change already. Even within the U.S., there's disparities between high-income communities and lower-income communities as to what the impacts are. Things like Hurricane Harvey in Houston, where it just sat and rained over Houston. For the most part, if you had thought about it when you were buying your house, you didn't buy it in a floodplain, a low-lying area. And a lot of times the people that can make those decisions based on more complete knowledge tend to be those who are more advantaged in terms of. So is Nebraska climate resilient? Short answer, nah, not even close, right? We don't have a state action plan that even takes into consideration what we might do to cope, adapt to climate change that we're going to have. The state doesn't have an action plan. I don't see one on the horizon. City of Lincoln does have an action plan, but that's one with the dot. Nebraska. The city of Omaha just put out a request for proposals for consultants to develop a climate action plan. And I'm talking just like, 10 days ago. And so they haven't even gotten responses from people yet to see what they might put together. But it was just put out. I wasn't even sure. I kept finding, I knew it was coming. The news reports were, yeah, it's gonna come. It's gonna come. It took me forever to find the actual RFP, but I did track it down and did actually go out there. So hopefully people will start responding. What are some of the resources if you're interested in climate resilience? The U.S. Climate Resilience Toolkit is an interesting place. You can look at climate information there. You can find some ways to deal with climate changes. The Model Forest Policy Program is a pretty interesting place. Climate Solutions University is an interesting thing. And the Resilient Rural America Project. A lot of times people think that, okay, I'm out in the country, I'm going to be okay. But no, the rural community is going to have issues as well. The Center for Climate and Energy Solutions, which started out as a Pew think tank, it's spun off, and it's got a lot of good interesting information. Now, as Kevin introduced me, I am the chair of the Earth and Atmospheric Sciences department, so I have to have an advertisement. Okay, I want you to remember that just a year ago, the Nobel Prize, well, to be truthful, half the Nobel Prize went to a couple of climate modeling pioneers, Suki Manabe and Klaus Hausmann. Now, Suki Manabe, I actually got to meet Suki, so I get to call him Suki because he told me when I was in graduate school. He was at the Geophysical Fluid Dynamics Laboratory in Princeton. And we went up as a group and we spent an entire afternoon with this guy. Brilliant man, took the time out to meet with a bunch of graduate students from another university, and we spent the time. We had tea with him afterwards, and it was wonderful. What a wonderful guy! And so he's a pioneer in climate modeling. He was doing climate models back in the days when we had rain coming out of the sky, and he's recognized. But atmospheric sciences is right for places for people who want to use the physics that they know, but don't necessarily want to go into what are possible or modern areas of physics. They want to go into applied physics. I always tell visiting students when they come to see me that atmospheric science, meteorology, climatology is treated as two different things. You could say it's applied physics or it's applied math. Take your pick, one or the other, right? That's what we do. Okay. And so there's a lot of areas where physicists, people who have gotten trained well in physics go on. We have numbers of graduate students from various physics programs all around the world, actually, come to do that. So it's science. I think it's a great outlet for them. Also, my other half, I'm also atmospheric and Earth and atmospheric science. So the Earth science is also applied physics, geophysics, geodynamics, hydrogeology. These all use physics to understand the processes that are going on in and on the Earth. So I leave you with some book covers that all have physics in the title, areas that we cover. I have everything except for the physics of the Earth on my bookshelf. I think I'm not a but if you want to check out our webpage, if you want to contact me, it's there. And if you have any questions, I'll be glad to.